Hello everyone, welcome to the third lecture of our machine learning course series. In this lecture, we will learn about gradient descent algorithm, its uses, why it is actually needed in machine learning. So, first we will look at the key takeaways. These are the key takeaways. First, we will look at the limitation of computation in machine learning. Then, we will understand what are optimization algorithms, why they are necessary. Then, we will see the challenge of multiple minima in cost function. Then, gradient descent, its concept and its intuition. Then, one of the most important things in gradient descent, which is learning parameter alpha. This is one of the most important things which actually the user or the model trainer has to set. So this is an important thing. Now, what about the limitation of computation in machine learning? See, when you plot a cost function, there are only two parameters I am showing here. In general, there are hundred thousands of parameters. So with these two, there are infinite values because see, if we are saying that theta 1 is a number, so even if it is a natural number, so natural number range from 1 to infinity. So if I take at random, now I have an infinite number of pairs, and these infinite number of pairs should be checked to know that whether the cost function is minimum or not. It will take a lot of time, and infinite computing power, and both of which we don't have. So we use optimization algorithms to effectively find and update these values so that we know that okay, this value, this pink value, is for sure is the minimum for this cost function. Now, this is the cost function here, and this is our objective. And we need to reach this objective accurately and in most efficient time period, or you can say in least time. So now, what are the optimization algorithms in machine learning? Optimization algorithms in machine learning is a method for finding a set of parameters that minimize the cost function. These update the parameters based on the gradient of the cost function. Now, what is gradient? Gradient is nothing but just the partial derivative of this cost function based on some parameters like theta I, where I ranges from I belongs to 0 to n. So, now to understand this concept, we will take an example concerning the parameters and will apply these optimization steps. Now, outline of optimization algorithms in machine learning. So, it is actually a two-step process. First, you will start with any random values of the parameters. Here we are taking two parameters, so theta 0 and theta 1. And then you will change the value of theta 0 and theta 1 such that the cost function becomes minimum. Now, how generally for parameters we take the value 0. You can take any value. It's just it is easy to initialize, so we just take 0. Now, what happens? Let's suppose you started from here. Hey, it is a maxima. So what happened? It the gradient will be calculated, and based on this, in next step it reaches here. So the cost function here has a lower value than here. So now our cost function is kind of less than previous one. We will do it again, 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 again. So it can move in any direction, but it will always be less than the previous one, and it will reach to the minimum. Now, one of the problems, if you see this one, let me highlight it for you. If you plot this in a 2D graph, let me show you here. There are minimum which are local minimum actually. Now, what happens when you have local minimum? Let's suppose you have a point here. The gradient will be calculated. Gradient is nothing, just the partial derivative, and partial derivative is just a slope. So let's suppose it came here, it came here, it came here, and lastly it came here. Now at this point, focus on this point. At this point, the slope is actually 0. Now what will happen when you will calculate the gradient here? The slope will be 0. When the slope will be 0, it will not move out of here. So we will be stuck at this point. This point is not the best solution we can have because this is the here the cost function has the least value. See, this is the difference. So we are kind of not finding the best value. This is actually a problem with many optimization algorithms. So we kind of prefer those algorithms which can come out of this state and can go in this. Now our goal is to find this global minimum. Let us see how gradient descent helps here. Now, that what I was explaining in previous, in it is now in 3D. What happens? You have started from different point, the gradient will be different, and we reached a different point here. Here we reached a different point here. From here we might reach here. From this point we might reach here. From this point we might reach here. So there is no perfect method here. Or you can say with this, the we can reach anywhere, and we always need to reach here no matter what. I don't need this local minimum points, I need this global minimum point. So there are many algorithms that do that, not only gradient descent, but gradient descent is kind of most popular and most used, so we are studying it now. Now, what is gradient descent? Gradient descent is one of the most basic and famous methods to optimize the cost function in machine learning. It actually uses the gradient of the function to gradient of the cost function to update the values in each iteration. It actually works in this parabola shape. So in 3D it becomes paraboloid and higher parabolas, but it is a parabola. So what it means is that it has only one minimum value. Now if there is only one minimum value, the concept of global and local is finished because there is only one. Now with this, I'm taking an example of only one parameter. Let's suppose our cost function is like this. So there is only one parameter to optimize. So that's why we have built this graph. Now there are three cases. The point at random you have chosen. It can be at this yellow point. It can be here in in this area, or it can be here in this area. So let's see these cases one by one. Now the case one, which is just you reached here, like you selected this point already. So it requires a lot of luck, and it is very rare. Almost 99.99% of time you will never encounter this case. And cases 2 and 3 will be the most general case, and you will try from these cases to reach here using the gradient descent algorithm. Now let's see it in detail. So what happens with this is a gradient descent code actually. Now repeat until convergence means that the minimum is reached where slope is 0. These are the slopes, these are 0. So now if we start at the left of the yellow value, let me show you this. So what will happen? The slope is negative, and here also a minus sign. So minus into minus, it will be plus. When it will be positive, so theta 1 will increase, which we want. Here theta 1 will decrease because slope is positive. So minus into plus is equal to minus. So theta 1 will be like theta 1's new value will be less than the previous value, and it will reach here. So in any case, the theta 1 is bound to go here, whether you start from here, whether you start from here. So now one of the most common error which happens in machine learning, or you can say in gradient descent, a lot of times, not just one time, even many people who have learned this algorithm make this mistake. What they do, they find the temporary value, or you can say the new value for a parameter, and then in the next step they update. It is not like that. First you have to process, you have to get all the temporary values, and then update. Why? Because see, we want that cost function should have a certain value at certain parameters, and then we are differentiating with different parameters to get different values. What happens with this? Now the cost function is changed. So how can you say, okay, I moved from this point? Because you have changed the point. So that's why we first process, then update. Now let's move on to next topic, which is also the last topic of this video, need of this learning parameter. Here in algorithm, you might have noticed that there is an alpha which is multiplied with this derivative, or you can say this partial derivative. So this alpha actually governs that how much of the effect of this thing, this partial derivative is there on the new value. Let's suppose the partial derivative comes as a 0.05. This is a very small value, and I think okay, it should be actually 1. So what I will do, I will multiply 20 to it. So this alpha will become 20. So this is what it do, it actually speeds up, slows down, or just decides the impact of this partial derivative on the new value, like how much impact should this have on the new value, or how much difference the new value and old value should have. It is one of the governing parameters in that respect. So it is generally represented by alpha. Now, with alpha, you can't take very small values, and also you can't take very big values. This is actually application dependent and data dependent also. Like if you use a different model, this alpha will be different. If you use some different data set, alpha will be different. So it is highly dependent on your data, and it actually comes with trial and error. You have to try and check that which alpha value is correct. So what it do is, if alpha is very small, it will take a long time to reach here. So we also have to optimize time. That's why we are learning optimization algorithms. So this is taking a very long time. But if the alpha value is very large, let's suppose alpha is 20, like in previous example I took. So what will happen? It might overshoot. It came here, it came here, it came here, and with this, let's suppose it came here. Let's suppose it came here. So it can happen that it overshoots. It never reaches this point, and we need to reach this point to reach convergence, because this is the point where the slope of the, you can say, the graph or the cost function is zero, and we need to reach the slope of zero to terminate, because it is a while loop, and it is a while loop written as slope is not equal to zero, and then the repeat until convergence code. So that's why we can't risk overshooting, and we can't risk very long time. Now, one may think that using this, that okay, let's suppose the point is here. Now, a large value of alpha can work. So you start with a very large value of alpha, or not very large, but a large value. Let's suppose this alpha equal to 20, and after 10 iterations, let's suppose in every iteration you are decreasing it by 1. So the d is 1, and you are doing this with every iteration. So after 10 iterations, what will happen? The new alpha will be 10. So some people suggest this, and even some algorithms do that, that they change the alpha in every step, or after some steps. This is actually not very kind of used, and even people don't prefer it, because see, if you have selected a reasonable value of alpha here, let me show you reasonable value of alpha here. What will happen is that, see, this function, let me write it for you, is not a constant. It is changing, and it is actually a decreasing thing. Why, you might ask? See, at here, this point, this is the slope. I have not drawn it correctly. Let me draw it correctly first. Here. So the angle is this theta 1. Here the angle is 0. Let's suppose theta 2. Here the angle is theta 3. So theta 1 is greater than theta 2, and theta 2 is greater than theta 3, this angle. But here you can see the theta 1 is actually greater than. In diagram it might not be like that easy to see, but the theta 1 is actually greater than theta 3, which is greater than theta 2. So see, the angle is decreasing. If angle is decreasing, the tangent or the tan of angle will be decreasing, which is nothing but the partial derivative we are taking. So if reasonable value of alpha is there, the my because this product alpha dj theta 0 to theta n by del theta I, this will be decreasing. So just you need this reasonable value of alpha here. See, even if some algorithms do change the value, these algorithms become fast. I'm not saying these algorithms have no use. They become faster, but the point is that they don't guarantee that minima you find is the global minima, and you need this guarantee. Yes, you can change these algorithms in a certain way. Many people have changed actually, and you can find a lot of research, or you can say a lot of articles about these algorithms, that okay, someone optimized this algorithm for certain application, but even that becomes application specific in many cases. So that's why gradient descent is used because it kind of applies to most of the applications, and also it gives the guarantee of this global minimum if alpha is correctly selected. And it's not a hard and fast rule that alpha should be in some range, so it is highly dependent on your data, how you process your data, how you actually use your data. So that's on the data and on the model that alpha value depends. So that's all for this video. If you like this video, do like, share, and subscribe to my channel. And if you have any doubts, do ping me in the comment section. I will try my best to solve the doubts there. And if the doubt is very large and I think that it can't be solved in the comment, I will make a separate video about it and make sure that the doubt is cleared. So thank you very much for watching the video. Thank you.